Hi everyone. So in this video, we're going to be talking about one of the main ideas of Calculus 1. And it's going to be kind of an introduction sort of broadly to the ideas that we'll be talking about in this class. So what we'll see is that the stuff we're going to talk about in this video, we're going to kind of leave it behind in the rest of the videos for this week, and we'll kind of come back to these ideas a little bit later. But I like to just kind of lay the groundwork for kind of the big ideas that you can expect to see this quarter in Calculus 1. So one of the main ideas of Calculus 1, and probably what I'd say is like the main idea, is this idea of the rate of change of a function and measuring the rate of change of a function. So let me write that down and I'll kind of explain what I mean by that, and we'll look at some examples. So one of the main ideas of calculus is measuring the rate of change of a function. So what do I mean when I say the word rate of change? Basically, it means how are the y values of the function changing as the x values change. So I'll write that down and then we'll look at some examples. So the rate of change, is basically how much does f of x, so f of x meaning the outputs, increase or decrease. So change, increase would mean it's going up, decrease would mean it's going down, as x increases. So it's kind of like as you're going from left to right and looking at your function, what is the function doing? Is it going up? Is it going down? Is it going up steeply? Is it going down slowly? Just kind of seeing what's the behavior of the function as you move from left to right. So for example, if you have a function that looks like this, so let's say that this is a function called f of x. This would be an example of a function that has a positive rate of change, because as you go from left to right, the function is increasing. So this is a positive rate of change. And similarly, if you have a function that goes down from left to right, so something like this, so let's say this function is called g of x. This would be an example of a function that has a negative rate of change. So we'll get a little bit more into this a little later, but why are rates of change important? Because they basically come up a lot in the real world. So for example, if you're looking at how far someone has traveled as time goes on, the rate of change is going to be their speed, right? Or if you have a graph that is the temperature as time goes on, the rate of change is going to tell you, is the temperature going up? Is the temperature going down? Or you could have a graph that represents population as time goes on. And then the rate of change would tell you, at what rate is the population increasing or decreasing. So that's why rate of change is such an important idea. It's just a really good way of kind of measuring different natural phenomena and describing like the behavior of population or temperature or distance or any of those things. So there's one kind of special example when it comes to rates of change. So calculus is going to really have to do with finding the rates of change of all sorts of different functions, but there's one type of function that we already know perfectly how to find the rate of change of that function. And so that type of function is a linear function, right? So if you have a linear function, so for example, let's say you have the function f of x is equal to 2x plus 1. So that's a linear function. It has a slope of 2 and a y-intercept of 1. So it will look something like this. So the rate of change of a linear function is just its slope. And the really important thing to understand about linear functions is that they have the same rate of change no matter what part of the graph you're looking at, right? So just to compare it to these graphs above, even though this one that we drew in green, it's always increasing, right? We always see it going up from left to right, but parts of it are steeper, other parts are less steep. So that's very different from a linear function, which is just literally always going in the exact same direction, the exact same steepness. So for a linear function, the rate of change is always the same. And what is that rate of change? Well, it's just the slope. So the rate of change is just the slope. So a lot of the stuff that we'll be talking about in calculus, you don't really need to use calculus when it comes to linear functions, because you can just say, oh, I just know that the slope of that line is 2 in this case, because 2 is the slope. So on the other hand, if you have a function that goes up and down and is different steepnesses, this one would not be a linear function. So for a non-linear function, so just meaning any function that is not a line, the rate of change is going to vary. So sometimes this function is increasing, sometimes it's decreasing, sometimes it's steeper, sometimes it's less steep. So it's fundamentally different from a linear function. And so in this class, we'll really be focusing more on nonlinear functions, because those are where we're going to really get into the more interesting ideas about rate of change. Okay, so basically for functions that are nonlinear functions, and this is what we're going to get into next, the way that we're going to think about their rates of change or kind of measure their rates of change is we're actually going to find a way to use lines to measure rates of change on nonlinear functions. So I want to sketch an example of a function, and we'll look at how we can use lines to quantify the rates of change of this function. So let's say we have a function that is a nonlinear function, so it's going to go up, and then it's going to go down, and then it's going to go back up again. And let's say this function is called f of x. So there's two different types of lines that we're going to use to measure rates of change for nonlinear functions. The first one is what's called a secant line. And this is something that we actually that you should have seen in your pre-calculus 1 class. So if you draw a line that connects 2 points in your graph, so I'm going to call this number here A. I don't know, exactly what these numbers are, but let's just say we have A and we have B. So if I draw a line segment that attaches those 2 points together, connects the point at an x value of A and an x value at B, this is what's called the secant line from A to B. So how would you find the slope of the secant line? Well, you would have to find the slope of the line the way you normally do. So how do you find the slope of the line? You do the change in your y values, and then you divide that by the change in your x values. So the slope of the secant line from x is equal to A to x is equal to B is f of B minus f of A over B minus A. So this might look familiar to you from pre-calculus, because this is the average rate of change formula. So all this is saying is that if you have 2 points on the graph, if you know their x coordinates and of those 2 points, you can find the y coordinate by plugging it in, and that's this, right? F of B minus f of A is the 2 different y coordinates. And then in the denominator, you're subtracting the x coordinate. So it's just finding the slope of the line segment between these 2 points. So the important thing about this, though, is to understand what this tells you about your function. It tells you the average rate of change. So this is the average rate of change from x is equal to a to x is equal to b. So, average rate of change tells you some things, right? It tells you that the general trend between these two x values is that the graph is increasing. But it doesn't tell you everything, right? It doesn't, provide you all the details of exactly what's going on. Because if you look at this function, it's increasing at the beginning, but then it actually starts decreasing. So when you find an average rate of change, it's not telling you all the details about exactly what's going on between A and B. It's just telling you like the general trend. So there's a different type of line that we can use to find a kind of more detailed rate of change, and that's what's called a tangent line. So a tangent line is basically when you go to your graph, so I'm just going to kind of pick a point on the graph, let's say maybe here, and I'm going to call that x value, let's call it c. So if you go to a particular value on your graph and you draw a line that basically just touches the graph, that kind of like imitates the direction of where the graph is going at that point, that is what's called a tangent line. So a tangent line is basically just touching the graph. It's not crossing through the graph. It's just kind of touching the graph at that point. So this would be the tangent line at x is equal to c. So the slope of this tangent line, that's what tells you basically exactly what's happening at that moment. So the slope of the tangent line at x is equal to c is basically, rather than being the average rate of change, it is the instantaneous, and I'll explain what that means in a second, instantaneous rate of change at x is equal to c. So what do I mean by instantaneous rate of change? It's basically kind of going back to what I was saying about this average rate of change business, right? So the average rate of change tells you the general trend. But if you look at what's going on this function between a and b, it's, it is steeper, then it becomes less steep, and then it actually starts decreasing. And the instantaneous rate of change basically tells you exactly what's going on at that moment. So just to give kind of another example, if we instead did a tangent line, let's say here. So a tangent line here would mean, again, you're drawing a line that's basically just touching the graph, kind of imitating. If you were to zoom in, you would want to see that that line was like really kind of imitating the shape of the graph at that point. So what we can see is that the slope of this blue tangent line I just drew is negative, right? So the green one that we drew has a positive slope, and so that means that the function is increasing at x is equal to c. But this new one I drew has a negative slope, and that's because the function is now decreasing. And if I did a tangent line over here, so that might look something like this. Well, that one has a positive slope again, and it's steeper than the one in green because the function is increasing more steeply. So tangent lines basically are a way of kind of quantifying exactly what's going on at that moment. And really the kind of reasoning behind it is that there's no such thing as the slope of a function unless that function is a line. And so you cannot talk about the slope of a nonlinear function, but what you can do is kind of imitate the shape of that function using a line and then find the slope of that line. So that's really what calculus is kind of all about, is using lines, and specifically using these tangent lines to kind of imitate the shape of the graph so that you can then figure out what's going on in terms of the rate of change at that point. Just to really quickly show you, because I think some students kind of struggle with how to draw a tangent line, I just want to show you what a tangent line doesn't look like. So let's say we're trying to draw a tangent line here. So this would not be correct. So why is that not correct? Well, because the tangent line shouldn't be going through the function. It should be kind of just touching it. So again, like that would not be a correct tangent line. The correct tangent line would be, you know, kind of just trace out what's the shape of the graph at that point, and then you can extend it from there. And it's possible that the tangent line might cross the graph somewhere else. So maybe let me draw an example that does that. So that could be like, let's see, I just want to think of a place I could draw the tangent line where that could happen. So for example, if I were to draw the tangent line like here, let's say, so that would look something like this. It eventually crosses the graph later on, but the important thing is that the place where you're drawing the tangent line, so the tangent line at a particular x value, it should not cross through the function at that x value. It might cross through later on, but it definitely shouldn't go like this, right? It should be kind of just touching the graph. Okay, so one thing I just want to tell you that might also help you think about what instantaneous rate of change is. So let's say that this function here represented the position of an object as time goes on. So for example, maybe you're driving a car and you're recording how far you've traveled as time goes on. So one way to think about the difference between average rate of change and instantaneous rate of change is that the average rate of change would tell you, what was your average speed throughout the trip. So, maybe you averaged 40 miles per hour over a certain time range. What would the instantaneous rate of change tell you? That would tell you at a particular time exactly how fast you're going. So you might have a trip where you're averaging 40 miles an hour, but maybe at one moment in your trip you're going 30 miles an hour, and at another moment you're going 52 miles an hour. And so if you had a graph that that gave you your position as time goes on, if you found the tangent line at different points, that would tell you your different speed at those different points. And so there's a problem on today's worksheet that is going to actually go through an example like that. So the last thing we're going to do in this video is look at an example of estimating what the slope of a tangent line is. So let's say that we have a function. So this function here is f of x is equal to x squared. So let's say that we wanted to figure out what is the instantaneous rate of change, or what is the slope of the tangent line. Those two things mean the same thing at a particular x value. So we'll see how we can kind of figure that out. So let me just summarize what we're going to be doing here. So how can we find the slope of a tangent line for a non-linear function? So why am I specifying non-linear? It's basically because if you have a linear function, this question wouldn't really make sense, because for a linear function, as we mentioned, the rate of change is always the same. So really the reason that you're trying to find a slope of a tangent line for a function is because you're trying to find the rate of change of that function. And so for nonlinear functions, that's where there's a little bit more work to do. So for this function, let's focus on x is equal to 1. So I'm going to start by sketching a rough idea of what the tangent line at x is equal to 1 looks like. So again, you want to kind of look really close to the point where you're drawing and just try to kind of imitate the shape of the graph there. So it's kind of like this and like this, something like that. I guess I should redo that because that didn't really look like a straight line. Roughly like that. So let's say we wanted to find the slope of this green line, the tangent line at x is equal to 1. So we could estimate it, right? Like, so in this case, you might say, okay, well, we know that we have this point 1, 1, and then it kind of looks, it's a little bit off, but it kind of looks like it goes through the point 2, 3. So you could estimate and say, well, it looks like the slope is up 2 over 1. It looks like the slope is 2. And that actually is the correct slope in this case. But the problem with that rationale is that you don't really know for sure 2 points that lie in your graph, right? So or on the line, in order to find the slope of a line, this is really important. In order to find the slope of a line, what do you need? You need 2 points on the line. right? Because then you can subtract the y coordinates, subtract the x coordinates. So for this green line, the only point that we 100% for sure know lies on the line is this point here. Any other point we're picking, we're just guessing based on the way that we sketch the line, right? But like, what if I sketched it a little bit different? You know, I might have said, well, it looks like the tangent line looks like this. And then I would have a totally different other point on the line. So you really can't trust that however you drew the line is 100% perfect. And therefore, you really only have one point that you for sure know lies on the line. So how are we going to get around this? We're basically going to use a series of secant lines instead. So what do I mean by that? Well, let's say that instead of trying to find the slope of this green line, let's pick 2 points that we do know lie on the graph of f of x equals x squared, because then we can actually find the slope between those 2 points. So let's say that we wanted to find the slope of the line between x is equal to 1 and x is equal to 2. So this is a line, this red line, that we actually can 100% for sure without any kind of error, we can figure out what the slope of that line is. And so why is that? It's because we know we're picking this second point so that it actually lies on the graph of f of x is equal to x squared. And so we can know hands down for sure what the x and y coordinates are for both points. So if you look at this red line, it does not have the same slope as the green line, right? It's a little bit off, it's a little bit steeper. But what we'll see is that if we can find the slope of this secant line and then find the slope of a different secant line where we bring this second point closer and closer and closer, the closer we bring this point in towards the point x is equal to 1, the closer and closer our line's slope will become to the slope of the green line. And if that's a lot to take in, don't worry, we'll go through it step by step. So basically what we're going to do is we're going to find a series of slopes of secant lines. So we're going to find the slope of the secant line from x is equal to 1 to x is equal to, and I'm just going to kind of leave this blank because we're going to do a few different examples. Oops, it's jumping around. So the first one we're going to do is from x is equal to 1 to x is equal to 2. So how do you find the slope of a secant line? Well, we do f of 2 minus f of 1 over 2 minus 1. And for this one, you can kind of just look at the picture and get it from there, right? So f of 2 is equal to 4, f of 1 is equal to 1, 2 minus 1 is 1, and so we get a slope of 3. So we know that that's an overestimate, right? We know that that's not the correct slope, but it gives us some rough idea of what the slope of that green line is. So how can we get better? Well, let's say that instead of going from 1 to 2, let's now go from 1 to 1.5. So that's going to look more like this. So if we find the slope of the line from 1 to 1.5, that, if we just compare what we had previously to what we drew now, it's getting a little closer. So before we find that slope, I'm actually going to show you on Desmos, I think, just to really help you see like what this method is that we're doing. Okay, so this is basically the exact same picture as what I had drawn. So this line in green, that is the tangent line. This line in red is the secant line, and so this point here is the second point. So notice that this secant line always goes through x is equal to 1. That point is kind of pinned down, and then I made it so that I can move this second point around. So the example we just did was with this second point at 2. And as we saw, the red line does not have the same slope as the green line, right? It's definitely a little bit off. But if we take this second point and we drag it to about 1.5, notice that now the red line slope is actually getting a lot closer to the slope of the green line. And if we bring this point in even closer, the slope of the red line is even closer to the green line. And if we bring this point in even closer, the closer we bring it to 1, the closer. So now I have that red point basically like just past 1. And notice that the red line is so close to the green line that its slope is going to be very similar. And so that's basically the process we're going to use. We're going to keep finding slopes of secant lines while taking that second point and bringing it closer and closer to 1 and kind of seeing what happens and seeing what the trend is with where those slopes are going. And by the way, why can't we just put this point on 1? Well, because then you couldn't find the slope. So in order to find a slope, you need to have 2 separate points. If you just said from 1 to 1, that you wouldn't be able to find a slope. So we do need to take that second point and we can bring it as close as we want to 1, but we can't actually put it on top of 1. Okay, so let's see what we get for this one. So in this case, we want to be doing f of 1.5 minus f of 1 over 1.5 minus 1. So finding the slope of the line in red. And if you plug that all into a calculator, you'll find that in the numerator, you'll get 1.25, and in the denominator, you'll get 0.5. And so that simplifies to 2.5. So not too surprising that as the line is getting less steep, we see that slope decreasing. Okay, so next, let's get even closer. So let's bring that second point now to 1.1. So I'm not going to really draw that because I think it would be kind of impossible to draw, so I'll kind of exaggerate it. I'm going to put it like here. But you can see that, again, like that little tiny line segment I just drew, if I were to extend it, it would have a slope that's really similar to the green line. So if we do f of 1.1 minus f of 1 over 1.1 minus 1, we would get, in the numerator, you would get 2.1. In the denominator, you would get 0.1. And so that is equal to 2.1. So again, it's getting even smaller, right? The slope is decreasing. So let's do one more, and I'm not going to change the picture because this one would definitely be impossible to draw. So 1.01. So we're now bringing that second point so that it's like almost directly on top of the first point. So if you were to plug this stuff into a calculator, you would find that the numerator, you would get 0.0201. And the denominator, you would have 0.01. And so that simplifies to 2.01. So what's happening with these numbers? So they are decreasing, right? We started with 3, then we have 2.1 or 2.5, then we have 2.1, 2.01, but they're not just decreasing. It's not like we have 3, 2, 1, 0, -1, right? They're not just getting smaller and smaller. They're specifically kind of flattening out towards a value of 2. Right? Because first we have 3, then we have 2.5, then we have 2.1, then we have 2.01. And if you were to actually keep going, so if you did this with 1.001, you would get 2.001. So it's not just that the slopes are decreasing, the slopes are specifically approaching 2, right? They're getting closer and closer to 2. So let's kind of summarize that over here. So basically what we're finding is that as we bring the second point closer and closer to x is equal to 1, the slope of the secant line gets closer and closer to 2. So basically from that, we can conclude, it's a good guess anyway, that the slope of the tangent line is actually equal to 2. So we can conclude that the slope of the tangent line at x is equal to 1 is 2. Because basically, again, it's like looking at this picture. The very last one we did, we had, a point that was like so close to 1. It was like here. So if the slope of that line was really close to 2, just looking at the red line and the green line, we can see that their slopes are so close that 2 is a good estimate for what the line is of the tangent, or the slope is of the tangent line. One other thing I want to mention, and I'm trying to switch this so that the secant line pops out on top. There we go. So one other thing I want to mention, and on today's worksheet, you'll have a question that asks you to do this. We also could have picked numbers that were below 1, right? So we picked like 2, 1.5, 1.1, 1.01, but you could have also done the tangent line or the secant line from 0 to 1, and then 0.5 to 1, and then 0.9 to 1, and then 0.99 to 1. It doesn't matter what side of 1 you're on. What matters is that you're picking values that kind of start a little bit further and then get closer and closer and closer to that original point. So this is basically the method that we'll be using for now, and then later we'll kind of refine this method and see how there's basically a nicer way to do it than just kind of plug and chug, plugging in lots of different numbers. So what we'll do is actually leave this video's ideas. We're going to kind of leave this behind for the next few days. And then next week, we're going to get back to this idea and kind of, again, revisit it with like a few more tools that allow us to really find these slopes in kind of an easier way. So just a reminder, there's a worksheet that goes along with today's video. Please do check that out. It will basically give you some practice with doing the same stuff we did in this video, and then also looking at an application to kind of a real world situation, which I think is really important for basically motivating like why it is that we're talking about these ideas. All right, that's it. I will see you all in the next video.